All right, what we want to prove here, it says to use mathematical induction to prove that the sum of the first n odd positive integers is n squared. So essentially what we need to prove is that when you add the odd numbers, 1, 3, 5, 7, etc., the answer is always going to be n squared, where n is the number of terms you're adding. Okay? So let's just explore where this 2n minus 1 is coming from. All right, so the numbers I'm adding are going to be 1, 3, 5, 7, 9, 11, 13, and so on. If I list the value of n, then this is n equals 1, 2, 3, 4, 5, 6, 7. Okay? How do we relate the value of n to the value of the term? Each time, how do these numbers relate? Well, if you look closely, you'll see that when n equals 2, the value is 3. When n equals 3, the value is 5. So if you multiply n by 2 and subtract 1, that's the value of your term. So that's why it says 2n minus 1 here. Okay? Questions here? Yes? Okay. Now let's see what the statement itself is saying. It says that if you add a certain set of numbers, the value is n squared. So suppose n is equal to 5. If n is equal to 5, I'm adding 5 numbers. So which numbers am I adding? 1, 3, 5, 7, 9. Okay? If you add that manually, what's the value? 25. Okay? The formula says that this value should be n squared, which is n equals 5, and that's n squared. Okay? Now, what if I add 6 numbers? Theoretically, based on the formula, without doing it manually, what should the answer be? 36, because if this was 5 squared, then this should be 6 squared, 36. Okay? So that's what the formula is saying. What we're going to do now is we're going to prove for the first case. What is the first case? The first case is n equals 1. If n equals 1, I'm just adding one number. What's 1? That's just equal to 1, which is n squared. So first I'm going to prove for the first case. Then some random case, n equals some number, and then the one immediately right after. Okay? So, let's see what we're doing here. The first case is n equals 1. You say there's only one term, 1. This equals to 1 squared. Is 1 equal to 1 squared? Yes, so that works. The second case is n equals k. Now, for this case, all you have to do is take the equation that you're trying to prove, literally copy it over, and just change n to k. So 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared. Okay? The next case is for k plus 1. So what happens if we put in k plus 1 here? Okay, and let's see what we should get. Okay, here n was equal to 5, and now we went to n equals 6. So this is k plus 1. If 5 is k, this is k plus 1. What did we have here? 5 squared. Now we have 5 plus 1, 6 squared. So we should get k plus 1 squared as our answer, right? Okay, so let's see if we're going to get k plus 1 squared if we do this. All right, so here we're going to add k plus 1 now. So we have 1 plus 3 plus 5 plus 2k plus 1 minus 1. Now, we're going to add to this the next number, okay? Just like here, we added 1, 3, 5, 7, 9, and then we inserted one additional number. That's what we're going to do here. We're going to insert one additional number. So what's that number going to be? It's going to be plus 2 times, not k, but k plus 1, minus 1. K is, sorry?
Yes, take the representation.
I can't hear. Yeah, yes. We're switching n with k.
Why?
Because n is the total number of numbers that we're adding. K is just some random one in the middle.
Right.
So this equals, now to keep this equation balanced, whatever we added here, we should also add to this side. So it's going to be k squared plus the same exact thing that we added here, 2k plus 1 minus 1. Okay, so let's simplify this and see where it gets us. So here I have 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus, I will keep this as is, 2 times k plus 1 minus 1 this time, equals k squared plus, distribute this, 2k plus 2 minus 1. Now this will be k plus 2k plus 1. Okay? So finally, if I copy all this over, 1 plus 3 plus 5 plus dot 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 2k minus 1 plus 2 times 2k plus 1 minus 1 is equal to, what happens if I factor this? K plus 1 squared. Right? So we proved for the first case, we proved for some random case, and we saw that the one right after n equals k gives us as a final answer k plus 1 squared, which is exactly what I was expecting. So now my proof is complete. Okay, time. Yes. Okay, now we're going to move on to example 2. And remember that there was a typo here and there was a typo in the first problem that we fixed. So those who didn't, make sure you fix it. So this was a typo. There was a typo here and we fixed it. Okay, here it's saying pretty much the same thing. First we proved the conjecture for the first odd numbers. Now we have to prove that the sum of the first even positive integers is n squared plus n. Okay? So again, let's just explore. I'm not going to start the proof yet. Let's just explore what this is talking about. Okay? If I want to list, first of all of the even numbers, and now if I want to enumerate it with n, so this is n equals 1, 2, 3, 4, 5, how does n relate to the term? Times 2. So this one here, when this is n, this is going to be 2n. Okay? So that's where this comes from. 2, 4, 6 plus blah, 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 2n is equal to n squared plus n. So what is that telling me? It's telling me that if I want to add the first 5 terms, right? What do I add? 2, 4, 6, 8, 10. Okay? If I add this manually, what does that give me? 6, 12, 20, 30, right? Now, what is the formula telling me? That it's supposed to be n squared plus n. If n equals 5 here, it's supposed to be n squared plus n, which checks out. Okay? So let's skip ahead. Let's say n equals 10. Now I'm adding all the numbers starting at 2 to 20. What does the formula say it's going to equal to? It's going to be 10 squared plus 10, 110. Now if I wanted to do the next one, I'm going to add all the numbers to 21, 22. Okay? What does the formula say it's going to equal to? 11 squared plus 11. So 132. Now, if we think in terms of k, so all I'm doing now is trying to get an idea of what I want to prove. What does my result look like? What should my result look like? If I think in terms of k, then, if this is k squared plus k, then what's this? From 10 to 11, it's k plus 1 squared plus what? K plus 1. So that's what my result should look like. Okay? Now, when I do this formal proof, my answer should look like this. So let's see if that is what we're going to get. All right, I'm going to try this for the n equals 1 case, because that's how induction starts. When n equals 1, it means I have one term, so I just add 2, and let's see if the formula checks out. 2 squared plus 2, no.
No, it's 2.
Oh, I'm sorry. 1 squared plus 1, because n equals 1. N equals 1. The formula says it should be 1 squared plus 1. And does that work? Yes. So it works for the n equals 1 case. Now let's see if it works for some random n equals k case. For this, what you have to do is just copy this over, switch all the n's to k's. So 2 plus 4 plus 6 plus 2k is equal to k squared plus k. Now the critical thing is the next step. For the next step, my n is going to be k plus 1. So to this, I'm going to add one more number. Just like we went from 2 to 20 and then to 22. I'm going to add one more number, the k plus 1 case. So it's going to be 2 plus 4 plus 6 plus 2k plus what? 2 times k plus 1. It equals, now k squared plus k, you add the same thing that you added here in order to make it balanced. Okay? Now what I'm going to do is distribute this. Okay? Now, I'm going to show you a trick. How do you know how to do it? Well, because I told you now that it's possible to do. Okay, so first I'm just going to switch the order of these two. So I'm just going to write it as...
Wouldn't k plus 2k just be 3k?
Yeah.
So it'll be k squared plus 2k plus k plus... Now, the 2 here, just for fun, I'm going to split it into 1 plus 1, because I can do that.